just schematically explain which figures we will be doing. So I will try to draw a zebra, or ask anyone to come and assist me, and we'll make a connection between zebra and nuclear magnetic resonance. It's an unexpected connection. Then there will be first, yeah, I think I can write. There will be an attempt to first prove that length of the spin vector is constant during the precession. And then the rest of the meeting will be to look for situations when a square is not constant. So it will be something very counterintuitive. If one wants to convert the equations that we are going to write today into the midway between everyday language and scientific language of equations, we are going to observe a thing that will look like length of spin vector can be shorter than h bar over 2. And its length will be varying over time. It's a complete heresy. We cannot say it this way, but it will look as if amount of quantized angular momentum will change. So it is a big wonder and surprise that we are going to focus on. So it will be derivations. Bless you. The main new idea that we are going to discuss is we will approach how to perform an average over ensemble. And this average over ensemble will lead to this counterintuitive thing. So it's not the spin; it is average over many spins can be. It's same like going from magnetization to like losing magnetization in heat. So individual spins are staying of the length that they need to be, but in average it is zero magnetization. And we are going to look into the dynamics. Then we will look onto modifications of density matrix and Bloch equation after average over ensemble. So averaged density matrix and averaged Bloch. So there we will introduce and observe new terms in the equation that I'm going to reproduce either from my memory or from the cheat sheet. There are only terms for accumulation of phase and excitations and de-excitations, right? And in the new version, there will be so-called longitudinal and transversal relaxation. And I do not count on my memory, and I just do not want to lie, but they're called T1 and T2, but I always forget which one is which. We will, as deriving, I will either recall or take it from the cheat sheet, but it is probably the notation that those who practice discussion of the NMR experiments did observe and did practice. Yes? No? Okay, if no, I will feel so happy of being the first who introduces. I thought there are some who experienced in the wet lab or characterization. So after So it is a long and ambitious plans, but we did a great breakthrough last time in this Google whiteboard, not Google, Zoom whiteboard. Amount of derivations will be, I would say, like 4 or 5 times less today, but the amount of ideas, concentration of new ideas per square inch will be higher. So we will be more discussing conceptual things rather than deriving equations. So after this, I'm going to practice my poor skills of drawing and draw sports arena, I don't know, stadium, arena, and runners, plus coach with gun. So it's even more surprising than zebra and NMR. And after looking on this image, we will come to the concept of 2 new effects that if you have an idea, you can speak up. I know that few of you know it. Yes, the effects in pulsed NMR. Like Steven, would you like to? Okay, so there are colloquial names for them in the NMR community. So one is free induction decay. And another is spin echo. And at the very end, I'm going to announce a couple of images that we are going to compute together at our tomorrow's lab. And they will be very like the lecture material and the lab exercise will match each other very well. So like lab or outcome. So we are describing the perturbed Hamiltonian in the interaction picture, which will be equal only to perturbation, and it will be basically time independent. We do have it as minus delta E over 2 plus delta E over 2 and positive Rabi frequency. Do we have over 2 in when we were discussing it last time? Me too. Our major outcomes will not suffer with or without 2. It's just an attempt to have a complete notation. So let's put question mark and fix it if needed. So
yeah, it's good.
Okay, thank you. Thank you for confirming. So if we convert this Hamiltonian into equation of motion, I'm going to draw something, write something very simple. So it is system of linear differential equations. I hope I didn't make errors in such simple equations. So in absence of external perturbation, where we introduced Rabi as transition dipole operator times electric field scalar product amplitude H bar as matrix element between 1 and 2. So in absence, if electric field is 0, you have only phase accumulation. It accumulates in different directions, forwards and backwards. And in presence of external perturbation, they change from ground to excited and back, Rabi oscillations. Then you did a tremendous effort. I keep very positive memories. It's one of the best things in my life when I only told a couple of words and the equations started going like in machine algebra computer code, like in parallel. Everyone started to follow the thread. It was really like a dream. So let's try to reproduce the result. So I'm going to start and then invite everyone to come and just add a couple of symbols and we'll cooperate. And the equation that we are going to draw is the main equation for the rest of the semester, so we cannot bypass it. We need to return to it again and again. Just in case you are questioning the motivation, why do we need equation for the density matrix? It is because we do want to describe average over ensemble and later interaction with the environment and thermal bust that leads to relaxational effects which are not available in the basis of wave function. So this effect, when length of the spin vector, average spin vector bar changes over time, is not possible if you have isolated single quantum system. So it is possible only in the language of density matrix. So we cannot continue without it. So we define it as ij as conjugated and unconjugated expansion coefficients of the wave function, and then we do have system of linear differential equations, or the time evolution of each element of density matrix is expressed as a linear combination of elements of density matrix themselves, right? So there are 4 by 4 16 elements in this matrix, and they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need to double the class, or everyone will do like maybe 2. So one needs to populate them by the elements that agree with this one. So delta E I H bar Rabi frequency I H bar, and some of them will be zeros, right? Also, some elements will be having positive and negative, and maybe before filling the table, we can guess. Oh, it is another little task that is agrees with your little quiz. To before after filling this table, it will be not valid. But before filling the table, guess how many elements of each nature are available there, right? So, Steven, would you like to try? Just feel anything you remember, and do not worry. It's just collective effort. Guess what in the first one? Does population of the ground state depend on the population of ground state if we do not have any relaxation and dissipation. So when we are in the limits of regular quantum mechanics, absolute value square is constant, right? Which means it doesn't depend on itself. So if it is constant, what will be the number there? Just zero, right? Okay. Yep. Thank you. So let's keep. You see, it's not complicated. Vanessa, would you like to? I know it is a quite a challenge to find a way. But move this one. There are more mechanical challenges than intellectual. So anything you feel comfortable to guess. So just symmetrically, which other things are expected to be independent? No, those will accumulate phase, but yes, here yes, it's very safe. Yeah, thank you. Initial attempts are much easier. It will be harder later. Well, would you like to try? And it is open book if you have some notes from previous time. And we all do remember how did we achieve to this equation, right? We just set up an equation of motion for dt applied to density metrics and then applied a derivative of the product. So it's all possible to derive. It's just take a lengthy time, and sometimes it is easier to memorize rather than to rederive. Yes, thank you for correction. Yes. Do you expect? I'm not sure. And so if we take 1, 2, or 2, 1 of diagonal elements, and they are going to accumulate phase. So here there will be something non-zero. But how about population of the ground state depending on the population of the excited? We do not have relaxation. We have only unitary Hamiltonian evolution. Yes. So we do row by column. Ding, 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 ding. So this one will correspond to contribution of row 2, 2 to row 1, 1. Mm-hmm. Halfway through. Yes, yes, yes. Oh, 0, 0, 0. You did, guys. You okay? Yeah, thank you. If you watched the recording, or if you were among those 4 who actively wrote these lines, you'll see how it comes from, right? And I will show a shortcut how to get to it. There is a way to rederive it based on the line 1, 2, 3, 4. 1, 2, 3, 4 from the bottom. if you look on the 4 from the bottom here, it shows a shortcut. And after we've done this little pleasant exercise, thank you all. You all will get very comfortable. Next. Yes, it's so good to be at the beginning of the list.
Yes.
Oh, you're welcome to do anything you like. Excellent. Yeah, thank you. Adam? Mm-hmm. I feel that someone is starting to observe the pattern. Okay. No. So what you are telling that the population of the ground state will accumulate based on the energy offset between the E equals omega of light minus E2 minus E1. So you're telling that if system is in resonance, then population of state 1 will not depend on the coherency. So you tell that if system is in resonance, the Rabi flips will stop. They will not stop. They will go proportional to Rabi frequency. Yes, but with different sign. Okay, yeah. Thank you, Patricia. Okay. This is, I can easily miss signs. I would put question mark and then look into the cheat sheet, but it's okay for the exercise. So yeah, thank you, London. David, would you like to try any, or keep sitting? You can delegate me what to write and at which spot. Okay, yeah, thank you much. So I think it is enough for the exercise. I will try myself and then look into the cheat sheet, but to my memory, the signs were similar. Okay, it is everywhere here the same. H bar. And then the signs were distributed as like plus plus, minus minus, minus minus, plus plus. But I can be poor in memory. I will double check with the cheat sheet. Now, the evolution of the coherency does depend on itself and accumulates phase O2 which bar because we multiply evolutions forwards and backwards, this over 2 disappears, delta E, and the H bar delta E. One has plus, another minus, and I will also pour in memory to recognize which sign. So it is or any cheat sheet, and there are zeros in here. So how many zeros? 6. How many Rabi frequencies? 8. How many phase accumulations? Okay. I think you are ready to do at least the half of the piece. And now I need to double check that we do not go too far in the wrong direction. I need to withdraw 2 points from myself. Minus here plus here. Those signs were guessed in the right way. Okay. It would be not unnatural to experience a little exhaust of this equation. By the way, by major off-diagonal or like anti-diagonal, there are zeros, right? If you need to feel it quickly. So I wouldn't say the equation is ugly. It's quite symmetric, right? But it is too much for a human being to memorize and write down every day, especially if we are looking for practical applications. So another thing that we have really gloriously quickly accomplished when we were here, not here, when, and I want to express my gratefulness that you all volunteered to join online lectures during the break. It's a really great investment into completion the course in time. So what we did last time, we have converted these 4 equations that look a little unnatural. They're quite natural if you work with them every day, but a little exhausting, in something a little more understandable. And what we did, we practiced adding and subtracting diagonal, and adding and subtracting off diagonal elements of density matrix. And then we found that maybe we didn't discuss it, but one can find that everything predicted by this equation of 4 complex value functions can be equally well described by 3 real valued functions. So we simplifying a mathematical problem, like right, even if you know some properties that diagonal row 1, row 2 must be real, but when we see equation, we do not know this answer from the beginning, right? But after little manipulations, this set of 4 equations can be of complex, can be reduced to 3 real equations, and projections of density matrix equations onto 3 real functions is known as Bloch equation. In fact, Bloch equation can be derived without density matrix. It can be derived as the expectation values of spin projections computed from the wave function. But as soon as we go to the average over ensemble and interaction with the heat bath, we should forget about wave function as much as we can. So it's just incompatible basis to speak about averaging and relaxation. I think no one will punish me for writing this one. And this thing saves me the 3 symbols. So if instead of spin component, I will factorize it as dimensionful Planck constant over 2 and so it's spin, and this is pseudo spin. The length of S capital will be 3/4 h bar squared, right? The length of S sigma squared will be just 1. So for humans, it is easier to draw a sphere of radius 1 rather than some combinations of Planck constant. So no one protests, right? So it's a legitimate substitution. Okay. When we practiced adding and subtracting the elements of density matrix, so rho 2 minus rho 1 over 2 will be sigma z, and we can always return back to correct dimensions just by multiplying by h bar over 2. If you just write long equations, it's healthier or just easier to skip dimensions. In the thing that we do in the lab, we are using atomic units, and Planck constant is equal 1 anyway. And if we subtract so if you are really emotionally attached to actual spin projections, you can say that it is 2 over h bar sz, 2 over h bar sx, 2 over h bar sy. Right? I didn't lie yet. So I do not want to repeat what we already did. I will just summarize the last equation from our last meeting online. So if one performs this, and by the way, to be complete, rho 2 plus rho 1 is equal 1, right? By normalization, C1 absolute value squared plus C2 absolute value squared equals 1, right? So formally, we go from 4 equations to 4 equations. But one of them is trivial, therefore we'll have only 3 equations. Now, sigma z ddt sigma x ddt sigma y ddt. Do you have any memories from? I'm not going to. We would spend too much time if you walk toward the board. But do you remember anything from our last meeting? No. It's possible to derive in 5 minutes, but you want to save this 5 minutes. So this one will depend only on one of other components. This will depend on one, and this will depend on two. So Sx, time derivative of Sx is coupled to pseudo spin y. The population inversion is coupled to population to sigma y as well, and sigma y is coupled to both sigma x and sigma z. The question is only what are the expansion coefficients. So I really do not want to rederive them, but if you feel lost and you want a little bit more comments, give me a little sign. Like if you don't want to disclose it in front of the rest of the class, please. Or like, so more comments are okay, or you're approximately following what is going on? Okay, so if we take rows of the equation at that part, like time derivative of row 1, 1, time derivative of row 2, 2, and then subtract them, then we will obtain an equation of motion for SZ, right? How it depends over time, and we can do the same for each element. So they are naturally connected, and by doing this exercise, we will rediscover what are the coefficients. So here is Rabi.
We might have a sign issue with the matrix.
Or?
Because going by the matrix, we should get 0, I think, for d by dt of sigma z.
They have opposite signs, right? So by
subtracting them, then they would all just cancel out, right?
Yes, no?
Oh wait, no, never mind. Yeah, no, yeah, we're good.
Okay, yeah. Thank you for trying to catch. Thank you, David, for following our discussion. And here we will have delta E over h bar, delta E over h bar, and there is a thing that I never remember, and why I need a cheat sheet to remember the signs. So it will be minus here and minus there. Right. So which equation is smaller? Full equation for density matrix or block equation? Right. So yeah, I think I need to finish zebra before the break, and then we'll go to average over ensemble. So this morning while preparing to the lecture, I was learning how to draw a zebra. And I learned that the lines change their direction. Maybe it's not an ideal zebra, but you'll forgive me. So what is the connection? Yeah, it should be a little more friendly. Well, I'll stop. So what is the connection between zebra and Bloch equation? Absolutely direct connection. They are very much, they are one-to-one transition. So let's analyze 3 cases of dynamics that governed by Bloch equation. So what Bloch equation tells us? How the pseudospin projections are changing in time. So the orientation of spin, if we speak about NMR, is magnetization. Along magnetic field SZ and across. And then over time, it may have precession. So 3 components that make trajectories. So we are going to study 3 situations. Delta E is not equal 0, but omega Rabi equals 0. So it's situation number 1. Then delta E is equal 0, but omega Rabi is not equal 0. In situation number 3, when delta E is not equal 0 and omega Rabi is not equal 0. Reasonable. So you have just 2 constants that govern the differential equation, right? And we can explore limiting cases. So first case, if we do not have excitation, if the system is left alone, it's like free evolution. Second case, if it is in the ideal resonance, so frequency of the incident electromagnetic radiation and own frequency of the system are the same, but ideal resonance is happening under irradiation. So irradiation is non-zero, so it's irradiated. And the third case, when everything is going on. So the goal of this exercise is to find the solution of the system of differential equations as function over time, right? So if we are in the first case, we can remove first equation, right? Because as soon as we get Rabi frequency equal to 0, we do not have mutual coupling between Sy and Sz. So we have only Sx equals minus delta E h bar sigma y dot equals plus delta E over h bar sigma x. I didn't try yet. No one caught me. Okay. So what is the solution of this equation, of the differential equation? So one can take a derivative of Sx, left and right. Then on the right, we'll have derivative of Sy. Then we plug in Sy into here, and we will have second derivative of Sx equals linear function of Sx.
Exponential.
It's all exponential, but if, once again, x double prime plus x equals 0. So if we have it on the opposite, minus x. If you do characteristic equation, the frequency will be plus minus square root of -1, which means it would be e to the minus I t plus e plus I at. So instead of exponential, it will be
Like sine cosine.
yes. So I think this is the only thing that one needs to remember from the course of differential equations. So if you have second derivative equal to the function itself, it will give oscillatory solution. The rest is very narrow, specialized details. Okay, so the solution for Sx for like certain reasonable initial conditions, one can of course make them summations of sine and cosine, but one of the solutions that S sigma x will be cosine of this delta E over h bar t, and sigma y will be sine of delta E over h bar t. And I have this is in the situation when originally we start at Sx sigma x equals 1, sigma y equals 0. So we do not have anything about Sz, which means sigma z is constant. It is whatever it was at time 0, right? Now it's time for zebra. I will leave less and less time, but so up will be sigma z. Here will be sigma x. There will be sigma y. Those are all expectation values. So we start, and it is pseudo spin. We skip h bar over 2. So we start sigma x equals 1, and then we have sine and cosine, which means we go the circular trajectory in case sigma z was 0 originally, right? But the solution doesn't tell what is the initial value of sigma z, right? So we need to draw a sphere, because up to now all solutions will be a travel on the surface of a sphere, right? And then the solutions for different values of initial point and initial different values of Sz will be a stripe, a line that goes across, a line that goes across like a meridian on a globe, right? Meridian on a globe. So three-dimensional object is covered by stripes. So it's a spherical zebra in vacuum. Okay? Corresponding to evolution of pseudo spin in time. Yes, please.
It's what we discussed last week when Lando was asked about the expectation value of X or Y bit transitions, and I said
Yes. You have a talent to. It's not a joke to write to ask right question in the right time. It will be immediately answered here. Thank you, Patricia. Okay. So and I don't know, probably you don't bother yourself with doing notes, but if you do notes, just draw a spherical zebra. So if we have this limit, then we cancel our second equation, because we do not have accumulation of phase, and we cancel the first term on the right of this equation. So we will have sigma z with dot equals omega rabi sigma y. And note, there are no imaginary units, and all solutions are real, right? Which is a little festival. So in second equation will be time derivative of sigma y equals omega r sigma z. Don't you expect similar solution? Sines and cosines, oscillatory solution in the minus here. I got it before you. So oscillatory solutions for Sy and Sz, right? And it will be same like Sv of t for specific initial conditions will be cosine omega rabi t. For sigma y of t, it will be sine of omega rabi t, right? And if you really are meticulous, we can make a general solution of sigma z equals initial sigma z times cosine plus initial sigma y times sine, if needed. One can do it. It's not a big deal. Now let's visualize the solution. So again, we have a sphere S sigma x sigma y sigma z. So and sigma x is equals to its initial value, so it doesn't change. So how do we interpret it? One of the solutions, if sigma x was 0 and we started, let's say, at the south pole, then we'll go from there to the opposite side and travel this way. But if initial value of Sx was bigger, if initial value of Sx was close to 1, it will be like almost a point. Trajectory will be like approaching, I would say, singularity. Just the circle will come into a point. If it is was -1, it will be also a point. But in between, it will be a trajectory that would also cover the sphere by stripes, but along different directions. Okay, so it is another spherical zebra in the vector. Okay? So all circles go in the plane YZ. Answer to London's question 2 meetings ago. All circles go in the plane XY. And if we have a more general case, then one needs to be a little bit more artistic than I can be. But so it will be sigma x, sigma z, sigma y, sphere, and the circles will be simultaneously in all planes along the axis that has some angle between z and x, depending on the mutual correspondence between detuning and Rabi frequency. And this is kind of general solution maximum that one can get out of isolated quantum system. Okay, let's announce a break for 5 minutes, and then I'll continue with other images and figures. If there are any questions, concerns, I'm here.
Can I have a very dumb question?
There are no dumb questions. There are dumb answers, which I can prove.
Trying to look at in what situation will you have the frequency to be 0 and the tuning not to be 0? It does make sense for me.
Huh? the first.
I'm just thinking, yes. I'm asking that in what situation will you have the frequency to be 0 and the difference in energy not to be 0? Because I was thinking that if you multiply the frequency and h bar, that's 0 times, it's supposed to give you 0, right?
Okay.
So
It's a perfect question. It is one of the smartest questions. Don't worry. So notations. Yeah, I'll put it here on a horseback. So we do have ground state. We do have excited state with energy E2, E1, and we do have frequency omega without Rabi. So delta E is omega minus E2 minus E1. Rabi frequency, omega Rabi, is it depends on intensity of electric field. So this is frequency. This is frequency of the field, and this is intensity of the field. So it's completely okay to have non-zero frequency, but zero intensity. It means like intensity is fading out. They're not in conflict. It's maybe if I would start using lowercase omega, it would be easier. But omega and omega sub r are very different things, and they differ by several orders of magnitude. So omega Rabi is, I don't know, in the order of between picoseconds and nanoseconds, and this this excitation frequency is like femtoseconds. Okay. So just a little exercise that will benefit right away. Let's. So I think everyone returned. So let's again. I invite you to catch any errors if you can, because I think this is. So if we need to find the total spin or total pseudo spin if you skip h bar constant, then before you were working on static aspects, but now let's see how the length of the total spin changes over time, and then we can practice derivatives if we assume that function commutes with itself. It's a dangerous thing. If needed, maybe one needs to do twice as more terms when they are swapped. If I fail in what I plan, I will need to redo it. So formally, one needs to do like derivative of sigma x times sigma x plus sigma x times derivative of sigma x over time, right? But maybe I will have a good luck this time with some simplification. So we do have equations of motion for pseudo spin depending on time, right? So I'm doing just a little numerical experiment to see what would happen if I plug in, if I replace derivative by what is dictated by Bloch equation. And after plugging in, I'm going to see and add together all terms. So minus 2 delta E h bar sigma y sigma x plus 2 delta E or h bar sigma x sigma y. Minus 2 omega Rabi sigma z sigma y plus 2 omega Rabi sigma y sigma z. So to be rigorous, and probably I need even to cut this part from the recordings because it is twice as cheaper than it should be. But if we add, instead of factor 2, if we add symmetric terms, they will have opposite sign and they will cancel in the same way as here. So if you add everything together, you see that there is a minus and plus. Yes, we see that these two terms cancel and these two terms cancel. Right? If we put, probably I should plus conjugate, Hermitian conjugate. And here again, plus Hermitian conjugate. So if one would open brackets as they should be, it will be same cancellation. But what would we discover? That it will be equal 0. So if we put the expectation values here and there, right? And then integrate equation. So then expectation value of the length of the pseudo-spin vector will be integral of 0 dt from minus infinity to t, which will be equal 0, or initial value sigma square of what it was at minus infinity plus 0. So it means the length of the spin is constant. And if you want to do total spin, it will be constant as well. Constant multiplied by Planck. So for the full spin, it will be 3/4 h bar squared. For pseudo spin, it will be 1. Right? H bar over 2 squared, h bar over 2 squared, h bar over 2 squared 3 times. And those are radius of the spherical zebra in vacuum that we all were drawing or imagining. Okay? So done with this, and we need to start, let's say, new chapter in a new direction. So we need to identify a situation when this is not correct, when the length of the pseudospin changes over time. So suppose we are in a little bit more real world than we were before. It means that any experimental sample is composed of many replicas of our system of interest. To focus on the isolated molecule is a very big deal. It's not possible when it's like microscopy or STM, and how do you know that you focused on the right molecule? So majority of experiments deal with macroscopic, or at least large number of any models. So instead of doing the diagram that I was drawing by demand of Patricia, I'm going to redo it. And if you were relaxing before, now I invite you to concentrate for like a couple of minutes. The rest will be just a consequence of this diagram. So instead of one two-level system, we will have many two-level systems. And each of them will have slightly different excitation energies. So if we modify the 0 point, it will be ground state of, and we can label them by some Greek letter psi, just something that is difficult to draw just randomly. Psi 1, psi equals 2, psi equals 3, psi equals 4, psi equals 5. So 5 systems, and in like 5 times Avogadro number in actual real life. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And labeling is not so important, so it will be E1 foci equals 1, E1 foci equals 2, E1 foci 1, 3, 1, 4, 1, 5. And they all can be equal 0. And here we have E2 for system 1, E2 system 2, E2 system 3, E2 system 4, E2 system 5. All of these systems, two-level systems, are being subject of irradiation by electromagnetic radiation of frequency omega. Right? But the detuning parameter for some of them will be 0, for some of them will be negative, for another of them will be positive, right? So we can call it delta, and I'll skip epsilon, just delta 1, delta 2. Here it's just nothing, delta 3, positive delta 4, positive delta 5. What should we do to describe such realistic situation? Of course, we can wait for another century for development of quantum computer, or just connecting all computers in the powerful network and simulate each of these systems on a quantum level and then add together. But at a time when theories were developed, and if you really want an Avogadro number, it still will be impossible, especially if they're coupled quantum systems, because the number of basis states, if one does it really, you remember, 2 spins has 4 basis states. 3 spins will have 8 basis states. So it's like 2 to the power n. And as soon as you get more than like 20 or 30, it will expire the limitations of all human petabytes on computers. So the natural way to save an effort is to practice an averaging. So we will speak about pseudo spin x, y, or z projection number I. I is x, y, or z. With another index, maybe I can put it on the top just to save space, for each system, right? And what if I commit a summation of all pseudospins, xi from 1 to whatever is Avogadro number, or whatever, how many of them I do have. And I can call it the sigma I with additional bar. So the bar stands for ensemble average. Ensemble average. So can we avoid computing Avogadro number of systems and just do 3 linear equations just for average pseudospin projection? And what would be the cost of this exercise? Likely, we will need to perform, to find average Rabi frequency, which can be the same if nothing changes. Very likely, we will need to have average detuning, which may or may not help. So we can define, and to have this procedure correctly defined, we need to normalize summation of ones from 1 to amount of objects. Same as you do in statistical sum in statistical thermodynamics. In this case, if we do not take temperature into account, it will be just equals to NA. But if they are weighted by Boltzmann, it will be something more complicated. Okay, so it's would define it this way. Then we would need same style definitions for summation of delta xi divided by summation of 1 over xi will be our average delta. And we can define, well, here in this specific situation, we are having the same frequency, but later on, to be without loss of generality, we can assume that if we have a big resonator and some molecules are close, some are far from the center of resonators, they experience different intensity of electric field, right? Closer to the edge of resonator, field will be 0. And therefore, they will experience different Rabi frequency. So omega Rabi sub xi divided by summation over xi of 1. So it will be average Rabi frequency. So the question is, what would be the consequence? Like if we carefully perform transition, if we merge together this definition and our Bloch equation, what would be the consequence and consequence? So can we just put a little bar here, there, and tell that it will work? The derivation is a little extended, and I will bring in a phenomenological thing, which later on we will, I wouldn't say prove, but we will illustrate that it is indeed correct. So benefit of, so we perform transition from individual to ensemble. It gives definite benefit that we keep very condensed, very small amount of equations. We still can do it even without computers, pen and paper for like 3x3, 2x2 matrices. One can predict everything. And in fact, this area of knowledge was studied well in like 40s, 50s, 60s. So most of the solutions that we are studying are unknown. We just need them as a foundation. But is there any, so there is a benefit. So few equations. But some people think that free cheese is only in mousetrap. Like, what is the price for this benefit or shortcoming of this price? So there are 3 additional terms. I'm right. Here is average delta. Here is average delta, which we defined, right? And for x and y, we do have a term proportional 1 over constant, which one? Proportional to itself, sigma x. sigma y, and this one decreases as 1 over t depending on itself. So those three additional terms are price for simplicity of the equations. So this frequencies or energy differences with bars are defined here. What I would need a help with is from the class and from myself. I'm always mixing this indices 1 and 2 in their names. So let's try to identify the logic. So maybe I was already wrong, and this could be named as 1, and this could be called as 2. So it is something to double check. And one of them is called longitudinal. And another is transversal. So I guess that if we remember the spherical zebras in the vacuum, and we have spin axis SZ parallel to external field, a long field. So something that corresponds to change of SZ should be called longitudinal, and those two that are orthogonal to it would be transversal. Here we have frequencies, and here we have 1 over periods, which is also frequency, right? So what are the consequences of having these equations, of these terms in the equation? So it couples the function, the derivative of a function, to itself, right? The sign is negative, like x dot equals minus x, which means x will be x of 0 minus t, right? Or over the capital if you have it here. So there will be exponential decay of all projections of pseudospin. So as a price of describing ensemble of spins with a single set of Bloch equations, we will automatically get an effect that length, that the diameter, the size of spherical zebra in vacuum will shrink, or the vector pointing on the state of pseudospin will shrink and point spaces in more and more closer to the center of the sphere. Bless you, bless you, bless you. So it's same like instead of traveling on the parallel meridian of a globe, we decide to play dwarfs and start digging silos deeper and deeper underground. One can try to imagine what it would be, but the solutions will be spiral, so it would be like coming inside, right? So whatever we do, at the end of the dynamics, the length of the pseudospin vector will be 0. The question is, well, one would want to rigorously derive this thing, but another thing would be to, if you already believe it, how to find the values of T1 and T2, how to find them maximally correctly, so that solution derived by solving single equation will be maximally equivalent to summation of independent equations. There are effects that are not caught by this simplified equation. But in some limits, they provide both types of solutions are very close. And in those cases, we need expressions for T1 and T2, for transversal and longitudinal relaxation, how quickly zebra shrinks. Okay. I'm going to move to another board and do a little derivation. We have plenty of time and we will finish in time. It's not long, but there will be again a few ideas rather than pure derivations. So we kind of agreed that this is proved. We introduced average over ensemble concept, and we defined this longitudinal and transversal. And it is my time to prepare to draw sport arena, runners, and coach with a gun. So we agree on this. It was our definition. We can define it from the very initial step just by using wave functions and definition of spin and pseudo-spin operators. Which means that if I solve an equation for either this or this, I can find density matrix of diagonal elements. I can find sigma x. Rho 1 equals rho 1, 2 is conjugation. Do you believe this? Anyone doesn't? Anyone needs a proof? So delta is omega minus E2 minus E1 because we are in the interaction picture. The C1 of t is C1 of 0 e to the minus h bar E1 t, C2 of t, C2 0 e minus I h bar E2 t. If we put star, it changes sign, then combining this will give e to the power minus I h bar E2 minus E1 t. And if you go into the interaction picture, we'll bring in here the frequency. So as soon as we have solution, and let's consider a limit when external irradiation is 0. So we already prepared excited state and just look how system is accumulating phase. So we do believe that we can go from this solution to sigma x. Now we do want to see what would happen for rho bar 1, 2, right, of t. So summation of xi, 1 over normalization, summation of xi, rho 1, 2, xi, and then here e minus I delta xi h bar t. One can replace in summation by integration. I am going to walk to another board and define limits of integration. Or you can just look there and tell it by words. You can define the range of integration as from minus delta naught 2 to plus delta naught over 2. Minus delta naught over 2 plus delta naught over 2, which means we limit that all our two-level systems are spaced in the limit from delta naught over 2 to plus delta naught over 2, which means the width, we have fixed density of states and they are distributed equally. Then we have d delta rho 1, 2 of 0, which we can assume was the same, let's say 1, and then E minus I h bar delta t. So when we see integral like this, it's very natural, intuitive wish to integrate over time, right? But here we integrate over frequency, over energy. So if you would have more time, it would be a great option to walk and get extra credit, but let's just get quicker. Although who knows, maybe you will do it quicker. So how do we take this integral? We need to make sure that the argument of exponential and the everything, this thing under differentiation variable are the same. If they're not the same, we need to multiply and divide by constants to make them equal. So 1 over n, we can put it outside of the brackets because we believe it's not, there is no distribution, they are the same, minus delta naught over 2 plus delta naught over 2. And then if I want to have d I t delta over h bar, I need to divide it by or multiply it here by h bar, divide by I, divide by h bar, right? And then I rewrite here E minus IT delta h bar. No errors yet. Could be variable u, integral E u du. So the integral of exponential is exponential, right? So we have e to the minus whatever we have here, t delta h bar, and when we plug in the limits, exactly, because we subtract upper and lower limits, yes, and then we have different sign, plus I t h bar delta naught over 2. And then here we have h bar, it, normalization constant, initial condition. So how do we treat this combination of two oscillatory exponentials? What is it? Sine. And if you have plus here and minus there, probably minus sine, right? You can like put 2 and 2. Then we will have h bar t 1 over n. 1 over n will be combined with this one. We don't need to write it explicitly. The averaging includes normalization. And then we do have minus sine of so we have sine of width of the distribution for all elements in the ensemble, times t divided by t. Okay. So once again, it's an amazing result. We did derive how the element of density matrix depends on time upon averaging, right? So we need to draw and imagine this this function. Delta t divided by t. So sine is 0 plus delta t plus delta third t third over 6 divided by t. If we carefully draw this function, it will show the, so it's a linear decline, 1 over or t decline, and then oscillations originating from sine function, right? So if we wait for certain time, if we wait for a half period, it will come to 0. It's not yet sigma, it is rho 1, 1, 1, 2 of time average. So we may find at which time the amplitude of this oscillations will first time will approach this for the first time. So we can just tell that delta t equals pi, right? And the time when it will come to 0, it will be the transversal relaxation. Transversal. So we can say that transversal is pi over delta naught. So the larger is distribution of frequencies. If delta naught goes to infinity, then transversal time will go to what? If delta goes to infinity, then time of relaxation will go to 0. If the distribution of frequencies goes to 0, transversal time goes to infinity. So it depends on the how wild, how broad is distribution of frequencies in the ensemble, the relaxation of the rho and 1 and consequently Sx, Sy will go quicker or slower. And by analyzing density of states, by analyzing frequency distribution, one can immediately get at least one of the relaxation times. So in the thing that we do for like research for living, our goal is to find Redfield tensor and rates of relaxation, and here is one of them. Right? Typically, we skip coherences in density matrix. Therefore, it's skipped for our everyday exercise. But if you would do full density matrix, this average distribution of frequencies of in the ensemble would immediately give an important constant for the relaxation. So a time for additional drawing. There is an effect that has been skipped is not possible to describe by this averaging. There is an effect that mandates explicit use of each individual spins. And before before or instead of going to this effect, I will draw two figures. One will be just regular Bloch sphere, and we can assume that each spin was irradiated by a pulse, according to pulse area theorem, which with the area equals pi over 2, which means that we will move from the south pole to the equatorial point. You can believe it, right? And if you have more than one spin, each of them will go to the same point. You have distribution of ensemble that is prepared halfway between ground and excited on the surface of a sphere, right? It doesn't contradict anything we discussed before. Now, let's, instead of each spin, we will assume little runners. Okay, so this circle will be a sport arena. Okay, and the path that they will go if we put no pulse and we just let them to accumulate phase, it will be just their track that they need to run across. So here is a sport arena. Here is the start point, and I do have a quick runner. Who is very energetic, maybe a slow runner who just walks, and an average runner. Then we do have a coach who has a gun just to give a signal that let's go. Okay, so they all lined up and ready to go. Then the coach discharges the gun, and they all start running on their track. So the quick runner in a certain time goes as far as possible. So his velocity of quick times time gives how far he will advance. The slow runner will get to his own v slow times time level of advance. And the intermediate runner will be somewhere in the intermediate. It's all understandable, right? Before starting the competition, they made an agreement, a treaty, that when the coach discharges gun for the second time, all runners must stop, turn around, and run back. Okay? So if they turn around, they will go with minus VT, right? And if one waits exactly the time interval between initial and first discharges of a gun, the quickest one will go to the same path and just finishes here, right? The slowest one will also, because he goes with his own velocity, he will point out at the start point. And any of them, because they have their own pace of running, they will return to the same point at the same time. So they will meet each other. Before they are distributed along the stadium, and if you do a scatter, like expectation value of their position, it will show to the center of stadium. Like average spin collapses into 0. But if we let them run back, they will consolidate and the expectation value will be large again. So I'm going to share screen and show a couple of illustrations. Okay, so here are your quick runners, right? Or maybe slow runners. And here is what we are going to do in the lab. So one can arrange two types of pulses, one more than two, but two important types of pulses. Pi pulse, if the blue line goes so completely to 0, means ground state is completely depopulated. Red line gets fully 100% excited. So we move on the sphere from the south to north pole. So pi pulse. If we do have half of this, so if the pulse is shorter in duration twice or twice is smaller in amplitude, then the initial gets depleted by 50%, and final, the excited state gets raised by 50%. So we find it 50-50. So it is halfway from south to north pole, and it finishes on meridian, right? So if one comes to, if one prepares the system onto the so if one prepares the system in this 50-50 distribution, but repeats it for like 10, 20, or 100 of spin 1/2 systems, there will be distribution, each of which will accumulate phase with slightly different phase. And if one converts their phase accumulation into the projections of the Sx and Sy, or rho 1 to rho to 1, which are also coming to 1/2. So those green and those lines correspond to rho real imaginary part of rho 1 to rho to 1. They are opposite. And then for populations, nothing is changing. But for the coherences, they evolve, each of which with their own pace. And if we make an average over ensemble, so this solid dash line would show the same trajectory that we predicted here in class. So it will be sine over t, sine delta t over t. And at some point, it will come to 0. So it will still be on equatorial, but it will, in spiral way, it will come to the center. In case, so here we do have this average trajectory of the lengths of the pseudo spin average pseudo spin vector. So it comes to 0. But if after a specific time we give a pi pulse, it means they go across the globe, and it efficiently corresponds to all of them starting to accumulate phase in the opposite direction, running backwards. And if one counts delay time once again, they will automatically rephase, and the length of the Bloch vector, pseudo-spin Bloch vector, will come back to its original value. So it is a demonstration where procedure of processing an average pseudo-spin value doesn't work. So to this effect is observed on experiment, and it is in the core of a lot of pulsed NMR and pulsed optical spectroscopy. The name of effect is photon echo, and this effect cannot be caged by an averaging. The free induction decay is easily described by this average procedure. For getting an echo, one needs to average over ensemble in a most rigorous way. I think it is enough. Thank you much for investing your time and sitting over time.